I do hope the connection is much better. It seems as if audio is going through now. Let me know if you can hear. I have been having like a real bad evening. I have been trying to get on to no avail. Not too sure what's happening, but I've been trying. If you're on and you can hear me, let me know. Can you hear me? Can you hear me wherever you are? Can you hear me? All right. Can you hear me from wherever you are? I'm not too sure what's happening. Good night, sir. I can. Okay. Wonderful. Nicholas. Good day. Nanko. Nanko, are you Jamaican? Nanko, are you Jamaican? No, you're not Jamaican. Where are you from? Oh, you're Trinidadian. Wonderful. Welcome, welcome, welcome. We are trying to understand our reach. So we try to ask persons whenever we see a new name where you're from. Hope you're not intimidated by that. It is just to ensure that we understand where our friends are from so that when we speak, we can speak, of course, with great clarity. I can refer to you. I can say my Trinidadian friend. This evening is not a wonderful evening for us. Please do not use it to judge us. We have been having a whole lot of technical issues. However, we are insisting that we're going to even do half hour of show with the students who continue to wait for us. We have logged on about 6 times. We've been trying to log on since 5, and we've not been getting through. This is a new link that I have sent to my students and to the fans. I'm hoping that they will be on. So I'm seeing Nanko. Nanko is from Trinidad. Welcome. Otisha Gray was here. She's from Guyana. Our St. Lucian, they were also here. And also those from St. Vincent, they were here earlier. I hope that they will rejoin. It's okay, sir. Everything will be all good. All right. But I still have to wait on everyone to come on. So I'm waiting. I know that a lot of persons might be frustrated. I wouldn't want to go through with the topic. They've been asking me, Otisha, you're in. Wonderful. They've been asking me to go through genetics, and I really want to do that. Now, how I started the show when I started just now, I'd asked you to go onto YouTube, open another window with YouTube, and I wanted you to type in 37 year in prison or type in Archie Williams. He's on America Got Talent. We wanted to lay the foundation as to why we should actually study genetics. For a lot of students, it's just a series of crossing lines and some fancy terms that no one seems to understand. So I wanted you to watch that. Then on your return, we'll have a discussion around that. And then we are going to hop into genetics, where I'm going to be going a little slower. I think I understand where some of the missing link is, and I'm going to be plugging those so we can move on and be pretty comfortable with the topic. I'm not sure if everybody will be back. We had about 30-something persons earlier, but then this on and off, on and off, on and off persons might be a little fed up, but I trust that they will rejoin. All right, so big up yourself, Nanko. That's how we talk. That's a Jamaican Creole. Big up yourself. It means that you are supposed to take care of yourself. It has a whole lot of meaning. It means that we're happy to see you. It means that everything is good. That one statement has a whole lot of things attached to it. But it actually means everything that is good and pleasant that you'd actually wish for someone. When it's one of those terms that are statement that we use when we are wishing each other well in Jamaica. It's a Creole. Big up yourself, man. Yeah, man, go and bless up yourself and that type of thing, right? So we're saying we hope you're okay, and we really want you to take care of yourself and all that. All right, wonderful. Yeah, thank you very much. Yeah, it's the Jamaican thing, So we do a little of that here. So go on over and watch the video, and then you come back. We're going to do something this evening. If it means that I'm going to be here for 15 minutes, I want to ensure that I fulfill the mandate. It's always my intent to teach, free or otherwise, to teach. We're going to be here for 3 days per week. So we're going to be teaching. So go on over and watch the video. And when you're finished, just come back and say, sir, we have watched the video, and then we will move right along. If it's even to talk about what's new. Okay, his name is Archie Williams, or you could type in 37 years in prison in YouTube. It's an America Got Talent show that you'll be watching, and you'll get the story about this DNA thing and how it actually helped Archie, even after 37 years, to be free. All right, so I am Mr. Wilson. This is CSEC Biology HSB Live. I'm streaming live from Jamaica. And wherever you are in the world, I want to welcome you to the show. It's our weekly show. We have 3 shows per week. We have a show on a Sunday evening at 5, on a Wednesday at 5, on Friday, we also have a show at 5. Unlucky, I can't send it in the chat. Okay. So that is pretty much what we do. We're always talking about biology, and we always try to ensure that we integrate the Caribbean. Alina Johnson is here. Alina, you're from St. Vincent or St. Lucia. Just remind me, please. I'm very sorry. Nanko is from Trinidad. Hi, Alina. So Alina, I've been asking students to up on over to YouTube. Just open another browser, and I want you to watch on. You're from St. Vincent, wonderful. I want you to watch Archie Williams. He would have been incarcerated for 37 years. I'm trying to use it as a foundation to teach genetics this evening. I want persons to understand the importance of genetics and the role that they will play having completed studies in genetics. I don't want it to be just a class of crossing lines and that type of thing. I want us to look beyond this class into genetics. So you're going over to YouTube, you're going to type in Archie Williams. He's on America Got Talent, and you'll hear his story about how DNA freed him. It's probably one of the better things, one of the videos I use to start my class once I'm going to teach genetics. We want to have a good reason why we're going to learn genetics. All right, so up on over there and let me know. As soon as you guys are finished, just come on over. I'm finished, sir, and we'll go through the class and cover what we can cover with whatever time we have left in the class. I'm really, really sorry for the late start, but we've been trying from somewhere about 5 o'clock, and we did not get through. We had all sorts of issues. We made a lot of shows you would have seen, sent out a lot of links. None work. This is the best one so far, and we're most grateful. So while you watch your show, watch the video, I will wait on you. And of course, when you're back, we're going to hop right into the lesson. I'm going to interest you with some dominant and recessive genes, some things that you can see around you. I want you to be able to identify those. Now, in Jamaica, it is said, I have I don't have the facts. It is said that about 35% of the population is what we call in Jamaica jacket, meaning that the father would have experienced what we refer to as paternity fraud. I have no facts to substantiate that, but it is said, it is widely said, right? But if it is something that is coming from starting this government organization in Jamaica, then it could clearly mean that about 50% of us would not know our right father, because that information would have been just the persons who are recorded. But what about those who are not recorded? I don't know the data, but it is said that it is a culture in Jamaica. And if it is a culture with what DNA is and the many things that could happen having had the wrong father, then we must educate persons why it should be. All right, so we're waiting on persons to join us. We will be here at least until sometime 7 thereabout. And we really want to share in the conversation on genetics. We're going to be looking at a couple of crosses this evening. Not too sure how many we're able to do or will be able to do this evening. But what we're sure is that we'll be doing some genetic cross this evening. And I do hope that you find that video on America Got Talent really interesting, so that it can at least be that point where you will say, hey, I need to take this genetics thing serious. I need to have a better understanding of what is happening around me. Hi Kiki, how you doing? I'm very happy that you're in. Really, really grateful. Remind me, are you Jamaican, Kiki? Are you Jamaican, Kiki? So we have Trinidad in the house. We have Guyana in the house. The Jamaicans are also in the house. We have from St. Vincent, we have Miss Johnson in the house, and Kiki's joining us. Kiki, just remind me where you're from. We're going to be doing genetics this evening. We're late. I might have to schedule another show on a day that is convenient to you guys, because I think we're not going to be having any show for the Christmas speech. Oh, your Kiki's from St. Lucia. So St. Lucia is in the house. Seemingly, Grenada. Grenada is not here as well. So we have Jamaica in the house. We have St. Vincent in the house. We have Guyana in the house. Trinidad and Tobago, they are here in live and live in color. And of course, I said Guyana, and the Jamaicans are also here. So it seems as if everybody, all the countries who are usually here, they are here. And we're still waiting on the numbers to increase from the other Caribbean island. The number is a little low this evening, and it is low primarily because we've been having problems connecting. But it speaks to our commitment to reach you. We tried and tried and tried and tried, and yes, we're here. I'm asking my students this evening to go on over to America Got Talent on YouTube, type in Archie Williams, or 37 years in prison. It is a story about a gentleman who got incarcerated for 37 years and DNA finally freed him. What we're trying to do is to set that platform, set that tone to start the study on genetics. I want it to be more than just numbers and crossing lines, and more than just going to the biology class to do genetics to pass a subject, to genetics being a career. All right? That's what I'm looking at. Sir, I watched it. Wonderful. I am finished. Wonderful. How was it? How was it? You think it's reason enough for us to study genetics? Do you think it's reason enough for us to study genetics? Were you moved? All right, for those persons who are probably just joining, Marshall, finish. Ranique Marshall, you're Jamaican? Ranique, are you Jamaican? Yes, it is indeed sad. Ranique, are you Jamaican? If you're watching online and you're not locked and loaded, you're not able to be a part of the conversation, we do suggest that you subscribe, come on over, and let's have a conversation. Now, this evening, we're going to be looking at genetics, and I'm going to be starting again. This is probably the place that I teach the slowest. I'm known at work to be one of those bullet teacher, but here I'm very, very slow. I understand the difference that there is with students from different school, different background, different country. Yes, I could tell Ranique Marshall is Jamaican. It is a Jamaican name. I am glad he somewhat got justice. All right, yes, wonderful. I think I am really happy too. But I want to talk about, while you were away, I was here blabbing. And I was talking about the importance. Hi, Crystal, how are you doing? I was here talking about the importance of genetics. The genetics today, the DNA technology is used to free person from criminal charge. It is used to, of course, identify persons, right? It is sad, but there is this thing that we talk about in Jamaica. We call it jacket. It's paternity fraud, and it is a big concern. And then we have all sorts of criminal stuff that we have to use DNA to solve. This evening, I decided that I'm going to share with you some dominant and recessive trait. Some dominant and recessive trait. I think we have almost everyone in the house this evening. We have persons from Jamaica, persons from St. Vincent, persons from St. Lucia, persons from Trinidad and Tobago, persons from Guyana, and the participant, the number is really growing. May I apologize for the last time for the late start, but we had technical issues and we decided that we are going to be here for you, be it late or later. We are not going to give up until we would have gotten through. And of course, the persistent elders here, and we are here with you. So we want to talk about some traits. And I'm going to be taking off my glasses, and I'm going to be very serious. But when I talk about these traits, before I get to the board, I want you to notice, I want you to be seeing what is happening around you and be able to treat with some stuff. I am very passionate about genetics for a number of reasons. I'm passionate about genetics because of crime. I was always passionate about genetics because it seemed to be a difficult topic for a lot of persons. And I wanted to be that person to assist persons to understand. But I became more passionate about genetics, having myself been a victim of paternity fraud. Having been there to counsel persons, men, who would have found themselves in a position where they thought that a child was theirs, and of course later found out it is not. So to me, the DNA thing is personal. I'm passionate about it, right? Might I say, in no way do I support violence against anyone. Let me make that clear, so we can jump into the meat of the matter. So we looked at that show, and it showed us the importance of the DNA, the genetics thing. Now we are going to be looking at some dominant and recessive trait. Before we look at the dominant and recessive trait, it is very important that we understand what dominant means. Dominant does not mean it is the most popular thing, as most persons would have thought that 10 finger is the dominant trait. That is not what it means. What dominant means is that it is the allele that will make itself visible in the phenotype once expressed. What does that mean? It means that we spoke about homozygous dominant, where we have two capital letters like 2 capital T. That is homozygous dominant. So that would have meant that once a person would have inherited the dominant trait, the genotype, they are going to be having the physical trait, the phenotype expressed. And we looked at tall. Tall is not even the dominant thing. I think short is the dominant stuff. I'm going to go through them in a bit. So the recessive allele, or the recessive trait, is that trait in which you would have to inherit in its homozygous recessiveness. Now we are using letters now, and it's going to change as we go along. And this is a big problem with genetics. We are doing so many things that are really similar, and where we jump over the hurdle, persons don't even realize that we have gone over the hurdle. But I'm being very simple now, so follow me on the simple platform. I'll tell you when I change. So if we were talking about capital letters being dominant and common letter being recessive, in order for you to inherit that recessive trait, you would have to have 2 of the common letters, right? And that is homozygous recessive. So if we were using forever, let us say we are using F for fingers for the dominant allele. So capital F is the dominant allele for persons with 12 fingers. If you have 12 fingers, the dominant allele would have been F. Figurative here, follow me. However, if you don't have 12 fingers, then you would have been a recipient of the recessive allele. So we tend to have 10 fingers. Most persons have 10 fingers. But 10 fingers is, of course, the recessive allele. So it is not fair to say that the recessive allele is always expressed. No. If you have the dominant allele, because of what the definition says, once the dominant allele is a part of that individual, then they are going to show that trait for the dominant allele. So a person could have the dominant phenotype in two forms. They could have it at homozygous dominant, or they could have it in the heterozygous state. And what the heterozygous state means is one big letter and one common letter. It's the easiest way for me to explain it. All right? So I am going to be giving you some stuff now. And if you have problems, not cross as yet. No, let us deal with some other stuff. Not cross as yet. I'm going to be giving you some stuff now. And when I give you these, if you have challenges, I want you to write them in the chat so I can answer. So we're looking at dominant traits. Oh, wow, having an idiot. All right, the first dominant trait I want to look at is the widow's peak. Anybody know what widow's peak? Type in the chat. Do you know what widow's peak? Have you ever heard about widow's peak? Have you ever heard about widow's peak? Anybody? In the chat, let me see. No? All right, beautiful. All right, so let us go. I am going to be using myself to demonstrate, because this genetics thing, I can't continue to teach it abstract. You must know where you learn. So let us go. There are some persons with some little V thing right here. So your ear come out like a little V right here, so. V, it is called widow's peak. And that is what we refer to as, yes, it's widow's peak. It is a dominant trait. It is a dominant trait. And I'm going to be giving you a number of dominant traits so we can build on it. Now, the other trait that I'm going to be talking about is bend pinky. So this is your pinky finger, but some persons have the pinky bend inward to this finger. So there's a curve towards this finger. Naturally, some persons have that. Now, that is also a dominant trait. I'm going to tell you where I'm going with this. Now, if you do like this for me, when I teach variation, everybody has to do this in my class. Just clasp your hands like that for me. Clasp your hands like that for me. Just clasp it just like you see I do mine. Now that you have done it, I want you to tell me which of the thumb do you have on top. Now, you can see mine here. You can see I have the right on top. Right on top. So I want you to tell me which one you have on top. We're setting the foundation for the genetics class. I'm going back to scratch. Which other finger do you have on top? All right, so some person saying right, left. Crystal Mackenzie has left on top. Nicholas from Trinidad has right on top. Gray has right on top. Good. Good. I like what is happening. Now, let me tell you, if when you went like that, you had your left finger on top, it is a dominant trait. I soon tell you about the dominant trait. Follow me. I'm telling you I'm giving you a long list that when you walk on the road, you will know. Now, if you have, look at mine, unattached earlobe. So if I can push up my ears like that. But there are some persons who have earlobe that comes right down and come on. Do you know detached earlobe? Anybody? Tell me. So if you have attached earlobe, that is the dominant trait. If you have attached earlobe, that's a dominant trait. Yes, I know. I know about that one. All right, good. Now, if you are able to roll the tongue, if you are able to do that, that is a dominant trait. I'll continue. Now, if you look at my chin, probably you can't see it. There's a little sinking in your chin right here. Some persons, it's called cleft chin. It is also a dominant trait. Cleft chin, the sinking ear, is also a dominant trait. Let us continue. Now, if you have dimples, let us sink in here. Those are also dominant traits. Let us continue. If you are right-handed, that is a dominant trait. Dominant. If you're right-handed, dominant trait. If you have natural curly hair, that is also a dominant trait. If you have freckles on the face, that's also dominant trait. I could go on and on and on and on. Where am I going with this? I'm going to share my story with you. I share it with everyone. I share it with everyone. The first place that we are going to correct this problem of paternal fraud is to understand the trait that can be passed on. That's the first thing we need to understand. And we need to teach this in school. So, we said that if the offspring, and I'm using the same set of letter, if any of this is in the offspring genes, either the homozygous or the heterozygous, the offspring is going to show that phenotype. So let us go. I have cleft chin. It's a dominant allele. What does it mean for my offspring? Because I have cleft chin. There is just one problem that I could have. It might mean that I have cleft chin in the homozygous state or the heterozygous state. But if I were supposed to get a child with a woman that is recessive for cleft chin, I have the dominant allele. What is the likelihood of my child having cleft chin? That is some of the problem we try to solve with the genetic diagrams. But I'm going to make it a little more complicated. I have cleft chin. My wife has cleft chin. And I end up with a child that don't have cleft chin. And the two we have the dominant allele. Is that possible? Is that a case of paternity fraud? We don't know as yet. We're going to be doing the genetic cross for heterozygous to see if any at all, both parents having a dominant allele, if the offspring could come with a recessive allele, don't have cleft chin. Or if you are right-handed and your fiance is right-handed, and then the baby born using left hand. We're going to be looking at some of these. These are some of the things that we're trying to solve from day one when we look at the genetic diagrams. Now, a lot of persons are afraid to go there to talk about these things. But who is going to teach you if everybody is shying away? Let us jump into the lesson. Do we have any questions on the dominant alleles I just made mention of, those dominant traits? Just type them in. I'm going to be moving on now. If you have questions about those dominant things I just spoke about, type them in the chat. I give you a minute or two to type so I can answer and move right along. If nothing, we just move right along. All right. So here we go. No, sir. No, sir. All right. Beautiful. All right. So we understand the concept of heterozygous. I want to start there. we understand the concept of heterozygous. And when we talk about heterozygous, I'm still stuck in this TT thing. It means that one big T and one letter T. All right, it means one big letter and a small letter. It has nothing to do with T. Right? When we talk about genotype, it's just that one is big and one is small. And I'm teaching it the simplest way, overly modified. And then when we talk about homozygous, we're talking about two of the same letter, as it were. Right? Now, the representation of genes or allele can only be in this tree form, as it were, for this. See, they're going to be heterozygous, homozygous dominant, or homozygous recessive. Now, we're going to be looking at a recessive condition called albinism. When a person suffers from albino, or when you're an albino, it means that the skin would have lost pigmentation. And this is due to an inheritance of a recessive allele. But before I give you that bit, I want to read you a little thing I wrote here on my notes, and I hope you'll understand where we got this segregation thing from. It said that meiosis produces gametes with haploid number of chromosomes. What haploid means is half the number of chromosomes. Hence, it contains one allele from each parent. Then there is recombination at fertilization that produces a pair or produces pairs in the zygote. What does that mean? Let us move on right into the thing. Good. So we are going to use A for the dominant allele. If you have the dominant allele, it means that you have normal blood type. So let me define. Let capital A be the dominant allele. Be the dominant allele for, I want to say, skin color. And we're talking about albinism. So if you have your normal skin color, whatever it is, it's going to be this. But however, let common A, that's a common A, be the recessive allele. Common A here is a recessive allele. Now, if you are going to be albino, because it is a condition of recessiveness, recessive condition, you will have to inherit two of this small a. I'll write it over here. You'll have to inherit two of that small a in order to be albino. Are you with me? Say yes for me now. Are you with me? Or you don't understand? Are you with me? Oh my, they are sleeping. Not with me? I'm going to be doing the cross now, you know. Yes, you are with me. Wonderful. So I'm just going to turn the board upside down, and I want you to follow. I'm going to tell you what I have, and the fact that you would have watched my videos, you would have known how to do the cross. Whichever, whether you want to use a Punnett Square or you want to use the genetic cross diagram, you can. We are going to cross a normal pigmented person with an albino individual. So if we say that the person is normal, the person is normal, not a heterozygous person. So what that cross means is that the parent is going to be normal A, that is what the normal parents, and the albino parents is going to be that. Are you with me? Now here we have the diploid number of chromosome, 2n. All right, the full number. Following? Now, to start the cross, we have to go to the gametes. And once you start talking about gametes, then it's full time we understand the concept of meiosis. What meiosis will do will half the number for the parents. So if you have 46 here, they're going to half it, give 23. half the number here give 23. And what that results are, what it looks like here, is that we're going to break this away. We're going to have gametes. And that is why we can't start the cross here. So we come down and we're going to have one A there. And we come down and we're going to have another A there. So this is the gamete. That right here, let me just write it right in line. And that is N. So this is half the number. So it was 2 here, half the number. And then down here, we're going to have the same thing. Common A, common A. So we're looking at albinism. All right? So now we're going to continue this cross. We're going to continue this cross. And this is where, in the definition I gave you just now, this is where fertilization is taking place. And you're going to have recombination. So when there is recombination, then in the F1 generation, we are going to have the 2N, the full number of chromosomes. All right? So if you want to read that for you again, I'll read it as soon as I'm finished, that you can have a better understanding. So I tend to have this pattern that I cross. I usually just draw my 2 lines down like this. That doesn't mean that that is the only way. It doesn't mean that that is the only way. You could deal with the first and the last and all of that. So what I like to tell students to do, once you draw your line down, don't draw them like me. That is going to confuse you. All right, I was just showing you that you could draw straight lines down. All right, so we're looking at albinism. All right, looking at albino. So once you draw your line down, make sure that you carry down the letter. Now, they can only receive 1 from this side and 1 from this side. So then we cross over like that, and we get that. So that's the first, that's one possible offspring. Not the first offspring, but one possible offspring. And then, so this is finished because it has its 2. So recombination would have taken place. Here, where the lines are coming across, you have random fertilization. All right, so we have random fertilization taking place here, or some would say segregation. Then we are going to pull this line down again. And remember, as soon as you draw that line, you want to make that cross. And we don't want to cross it with this because this is already used on this side already. So we want to go over here. Might be a little easier there. And that is going to be the second possible offspring. And then we have 2 lines here, and each should have at least, I like to tell students, each should have at least 2 lines. All right, so each should have at least 2 lines. So 2 lines, 2 lines. This has 1, this has 1, this has 1, this has 1. So it means that we need to do something about that. So pull down another one, and we want to write the recessive allele. Remember, the convention is that the dominant allele is written first. Now, this is already connected to this. So we're not going to repeat that. What we're going to do, we're going to connect it to this on this side over here. All right, so we have the dominant allele first. Now, this is complete, this is complete, this is complete, this is complete, this is complete. However, this is not completed and this is not completed. So we need to treat with that. So come on down, do that. And it is not connected to this as yet. So we just go on down like that. And what you find happening is that we have this. All right, so this is the result for the cross between a normal pigmented person and an albino individual. Now, at the bottom here, so you observe that we have been labeling. So here we have the 2N in the parents. This is the full number of chromosome. Half the number here, we half it here. Then we have random fertilization. And then this is going to be your F1 generation, first filial generation, F1 generation, and it is, of course, the genotype. This is the genotype for the F1 generation. Remember, the genotype is usually represented using letters. Now, there are some cross that we are going to do that we are going to use standard letters, and there are others that you could just define and roll right along. Let us continue. So this we say is the genotype. That's a genotype for the F1 generation. The next thing we need to know is the phenotype. phenotype. But before we get to the phenotype, I want to introduce you to a new word. When we started, I'm going to turn the board around a bit. If you need to write something, let me know. When we started out, we spoke about, I'm going to put A's on the board now. So that was homozygous dominant. We said that this was homozygous dominant. We said that that was homozygous recessive. And then we said that this was heterozygous. Now, with inheritance of this recessive trait, what happened is that this remains homozygous dominant. This remains homozygous recessive. This is still heterozygous, but this time the individual that has this genotype is called a carrier. C-A-R-R-I-E-R. So this individual is called a carrier. What it means is that the individual who is a carrier, they will have the trait, but it will not be manifested in the phenotype. So what it means is that this person could walk around with it. Nobody knows that they have this problem, but it is right there inside. Now, why it doesn't manifest itself is because the dominant allele would have been expressed over the recessive allele. And that is why when I started out, I started looking at dominant and recessive allele. So the dominant allele would have expressed itself over the recessive allele. So the only way a person could have albinism is if they got too small a, the homozygous recessive condition or homozygous recessive state. So when we turn our board around and we look at what we have here, big A, little a, big A, little a, big A, little a, big A, little a, what we find out is that we have 4 individuals here and they all have normal pigmentation. They are carriers, they do have the trait, and you could continue with this cross to see if they could pass it on to their offspring. They have the trait, but nobody can say, yeah, you have the trait unless they do some amount of tests, because it is not expressed in the phenotype that which you can see. So now that we have done this cross for a normal pigmented person like myself, I think, and somebody who has albinism, I'm going to ask you now to do your cross, or I could just turn over the board and go again. Let me just turn over the board and I'm going to be solving the same question. Same question. So there we did some crossing a while ago. If you need to stop me, please type it in the chat. Don't allow me to go to yonder and then you don't remember where I should have stopped. So here again, we have the 2N for the parent. I'm going to go a little faster now. And then we have the gametes falling out here. That is N. And then we have the gametes here again. After which we have random fertilization. And we have that coming. Oh, no, that's not what I want to do. So now the gametes are here. What I'm going to use to solve it now is the Punnett Square. I do hope that you are seeing. Let me see what's happening here. Good night, sir. Sorry for being late. No, it's fine. It's fine. It's fine. It's fine. All right. So here we go. So we are using the Punnett Square to solve this. Some persons don't like all those lines. Now, the Punnett Square is just a rectangle. There are other types of rectangle that you can use. But the one that I use is this 4-sided box rectangle. And you just draw 2 lines across. Forgive me for the wave. And you draw 1 line down. 1 line down. If you know the parent sex, of course, the male is usually placed here. And you have to start to get used to putting that type of information in, that when you get to the pedigree chart, it makes it very easy for you to solve. So now we're going to put in this here. We assume that this is going to be the father. So we put One of the A here, capital A, the other capital A there. One of the common A here for mother, and one of the common A here. Now, to solve this, what we're going to be doing, I hope you're seeing, wherever these intersect, we're pretty much going to put the two letters. Remember, at all time, you are putting the capital letter first, or the dominant before the recessive. So there we go. That's the first one. So that is this and that, that and that. And here we go again. So that come down and that come across. And we continue in like form here. And again, we do that same thing here. And we end up with the same result. Now, here is where we would have had our gametes. So this is where we would have had our gametes. That's a 2N when we break away from the parent. This entire thing here is, of course, the random fertilization, right? So random fertilization taking place here. And then what we have happening is the genotype being formed. You could just write them down here. And of course, you could also write the phenotype. So of course, the random fertilization takes place here. And then you are going to write the phenotype that all the individuals have normal pigmentation. However, they are all carriers. Now, we're going to be using this carrier word again as we move forward with the genetic diagrams. Now, I am pausing here to accept your questions or your concerns or the emotional outbursts, but don't let me move forward if you can't do it. Now, I want you to do a cross for me. I want you to cross a carrier. Two carriers. So two carriers for albinism, I want you to cross them and tell me what the offspring, what the likely offsprings will be. So I'm leaving up one side here for those persons who probably want to look at what I had. All right, so I want you to cross for me two carriers for albinism. These are two persons who look perfectly well, and despite they are looking perfectly well, an albino child probably would have been a child of the union. So check that for me. Albinism, we're looking at crossing two persons that are heterozygous or two carrier for the trait, and we want to see what the offspring will be. All right, so I'm looking and I'm listening, and we're going to be working that out as well. So we are looking at albinism, and we are saying that with albinism, in order for you to suffer from that condition, you would have to inherit the genes, the alleles, in the recessive form. Remember that alleles are just alternate forms of gene, where we talk about fat and slim, tall and short, black and white, that type of a thing. All right, so you are crossing the carriers. And when you cross a carrier, we're going to get now back into that whole idea of a phenotypic ratio. All right, so I am waiting on you to give me that bit. I hope we're doing well. All right, so I want you to do that cross for me. Remember, we are crossing two carriers where we're using the big term now, so we're moving away from this heterozygous. And remember that carrier is not a term that is used with all the crosses. So we are looking at crossing for this recessive condition, right? And this recessive condition we're talking about is albinism. And albinism is a condition in which a person loses their skin pigmentation. All right, so what's the topic? What topic are we on? We are on genetics, and we are looking particularly at albinism, a recessive condition, and we're going to be jumping onto something else. We want persons to understand how to do the Punnett Square. We also want persons to understand clearly how to do those genetic crosses. It's very important that you understand the rules as we go along. If you don't understand the rules, as soon as we get into the Punnett Square, you're going to be finding yourself in serious trouble, and we don't want that. So how are we doing? I'm not seeing any answers yet. What is happening? What's happening? All right, so should I erase and start with the Punnett Square first? But you want me to start writing? Yes, no? Talk to me. I don't want to lose you. Yes, sir. Okay, cool. So I turn the board around, and I want you to just follow as I go really, really slow this time. So we are looking at a recessive condition called albinism. Albinism, albinism. All right? So we want to find out what is the likelihood, what type of children we're likely to have if we have two carrier for the trait having offsprings. So two carrier for the trait, we already know that this is going to be heterozygous. So it's going to be big A and little a, big A and little a. Now, these persons are going to look perfectly well. You won't even know that they have albino. They themselves might not even know, because in most cases, we're not doing any genetic counseling. So having done this, this is pretty much at the two end states. So I have the full number of chromosomes. Now, remember that in meiosis, we are going to end up having half that number. So meiosis taking place, that is going to half. So we're going to have that there. We're going to have that there. And I'm being very, very simple, but follow the practical on the board. We have that there. Now, that is pretty much the gametes. And that is how you are supposed to do it for CXC. Then we come here and we're going to have random fertilization. Random fertilization. So we are only able to cross this one time with this, that type of a thing. All right. However, the whole idea is that by we get to the F1 generation, we should have a recombination where we have now the full number of chromosomes again. So here we go. I like to cross it by just bringing down one like that. And when we cross it, we should always write the capital letter, write the associated letter, and then I'm going to be crossing over here. I'm going over here. All right. And then again, I'm going to be doing the same thing. So that's the first possible offspring. Then I'm going to be doing the same thing here. Right. And I'm going to be crossing like this. And of course, that's what we get there. Now, this person, now I won't tell you as yet. And then we want to come on down here. We have a capital letter. Right? And we already crossed this. So we are now going to be crossing that. Now, persons might choose to draw the lines differently. All right? But what we are trying to do is to get, at least in the layman term, at least two lines to each. So this still need another, and this still need another. So we're going to pull this down. Common letter there. And then we need to pull another one down from here. And we are going to get a capital letter. We always write the capital letter first. Now, what we're looking at, and remember, you know, when you do the cross, you might not get your common A's here. You might get them down here, but it doesn't really matter where you get them. What is important is that you arrive at the same answer. It's all about, remember we said that it is random fertilization. So of course the lines are going to be all over the place, and you are going to end up get things. Probably you get it here, probably you get it here. It doesn't really matter, seriously. What is important is that you, is that a real thing? What's a real thing? Lenny Cooper, what is it that you're referring to? What are you referring to? So we said that this is random fertilization. And this is going to be the recombinant of the F1 generation. Forget about the recombinant, it's just a F1 generation. My whole idea of coming to you with this recombinant and this 2N and all of that was for you to understand why we have all these different steps. But after you understand that we have all these different steps, you don't need to even think about that. So Lenny Cooper, is that a real thing? Oh, teacher, sir, you said always write the capital letter first. Yes, so I haven't done that. Yeah, as in where you have a combination, if you have a common and a capital letter, you are going to write the capital letter in front of the common letter. Not to say that this have to be over here and this be over there. No, that's not what I meant. Is that when they are beside each other, you write the capital letter first. But it doesn't matter if you have this over here. It's not wrong. It's perfectly well. The wrong table? No. You could use the genetic table if you wish. You don't have to use this diagram. I could turn around and do the Punnett Square just the same. But what you're observing here, when we started out, we started talking about some dominant trait and what the offspring should be. You are realizing here that these two persons are normal. They have pretty much the ideal skin pigment. But each time they have a child, there's a possible outcome that at least 1 out of 4, 25%, there's a 25% chance that if these two persons, these two carriers were supposed to have children, there's a 25% chance or a 1 in 4 chance that they are going to have a child that is albino. There's also a 25% chance that they are going to have a normal child. Look at this here. 25% albino, 25% normal pigmentation, but there's a 50% chance that the offspring might be carrier for the said trait, right? So here we have these two persons not knowing that they have the trait for albinism. They are carriers. They ended up having a child that is a albino, and the father might run away to say that, listen to me, it's not my child because look how I'm black. Where you get white pitney from? Now, in that case, you need to do some genetic counseling or do some DNA tests or something like that to ensure that you are not doing the wrong thing. All right, so let me see what's happening here. Genetic counseling. Tisha Gray, is so I did the table. So if so, I did the table wrong. All right, do we have any question on this? Everybody got this correct? If you got it correct, just say, yes, I got it correct. You got this correct? Guys, you have to get the basic correct before we can move into the bigger stuff. Everybody have that all right? Albinism, you can do the cross. It's too confusing. What's that? Okay, yes. Elena Johnson, she got that correct. Anybody else? Remember, if you are struggling with this diagram, you could always use the Punnett Square. And that is why the syllabus, I think, wants you to use both. In a matter of fact, as soon as you get to universities and you are studying dihybrid inheritance, what we're doing now is monohybrid inheritance. You are going to use the Punnett Square because you won't have space to do all these crosses. All right? So ensure that you understand this diagram if you are going to be doing sciences at universities, because when you do like dihybrid cross and trihybrid cross, you're talking about like 64 stuff. You won't have space on the paper to do it. You'll have to use a table like this. All right? Kiki, you don't understand? No, sir. Yes, sir. What is no? What is yes? Do you understand, Kiki? Do you understand? Is that a yes from you, Kiki? Is that a yes? I'm seeing yes, yes. So I think it is a yes. All right. So are we comfortable with that now? This is for everybody. This is a question that everyone will answer. I'll give you one other, and then we are going to move on. I want you to cross a heterozygous individual or a carrier I'm using the words. I want you to cross a carrier for albinism with a albino individual. So you're going to be crossing a carrier with an albino individual. All right. This time I'm going to be using the Punnett Square. Remember, the carrier with the albino individual. Now, so the first thing that you are going to do, you are going to identify the phenotype for the parent. And the phenotype I gave you that a while ago, I said that one of the parent is a normal pigmented person, but it's a carrier. And of course, the other is albino. That is going to be the phenotype. Then you are going to write the genotype. So I'm starting from the genotype. So here it's the carrier. And once it says carrier, I know that it is heterozygous. And if it said the person has albino, I know that is it. Because you can only have albino if you acquire in the recessive state, homozygous recessive. So this is homozygous recessive. So I also know that I can't start my cross here. So I must break away to the gametes. So I have that there, and I have that there. I have this here, and of course I have that there. All right. And then I am not so comfortable drawing all those lines, but I remember Mr. Wilson said I could just draw. Of course, you must write in what these are at the side. This is the gametes. And this is the parent genotype. By now, you should be comfortable with genotype and phenotype. So I remember that Mr. Wilson said that we're supposed to just draw a rectangle. So I'm drawing my rectangle like that. All right. I remember Mr. Wilson saying that. And then he said that I'm supposed to just draw 2 lines across. He also said I should draw 2 lines down. Then he said that I should separate this first cell here and identify whichever one is male. That represents male, and this represents female. And you'd want to know in some cases the exam paper will tell you, in some cases it will not. But if the exam paper doesn't tell you, you could just do it for yourself. Just decide which one you want to be, male and female. It doesn't really matter. Unless you are using like the X and the XY chromosome, then at that time it really matters. So here I'm going to be using the carrier as the male. So I'm going to be putting that there, and I'm going to be putting that there. And then I'm going to be using the female here as a person with albino. This person has pigmented skin. Probably I wanted a girl with very light complexion, didn't know anything about albino. So I chose this brown girl, and she's actually an albino. I only found out when I started having children that had her complexion and whatever else happened thereafter. So then we do the cross. Remember, where these intercept, we're going to write both. Where they intercept. So it intercept here, and usually we write the dominant allele first. Then we have A. All right. So then where these two intercept, we have 2 common A's now. 2 common A's, not a 9. These are common A's. And then we come here again, and we have a capital A. And again, we have a common A. And here we have 2 common A. This and this A both intercept here. So we ended up with that. Now, what I want you to do now, it's your turn. I haven't been talking much about the phenotype and all of those, about the phenotypic ratio, as the syllabus would have us explain. So I want you now, based on the fact that I would have done this for you, I want you now to tell me what percentage, let me just write this a little better. I want you to tell me what percentage of the offspring, the F1 generation, will suffer from, is likely to suffer from albinism. All right, so here's the board. What percentage of the F1 generation is likely to suffer from albinism? Please write it in the chat. I also want you to tell me what percentage would have been carriers. Write in the chat for me. So this is albinism that we just looked at. We just looked at albinism. I want you to